Section 15.4, Geometric Sequences. So, an example of geometric sequence could be 3, 6, 12, 24. So if I look here, to go from 3 to 6, multiply by 2. 6 to 12, multiply by 2. 12 to 24, multiply by 2. So this is called a geometric sequence. If there's some constant r such that the n plus first term is equal to r times the nth term. Usually we make the assumption that a sub 1 is not 0 and that r is not 0 and r is not 1, just so that these won't be like trivial or constant series. So a geometric series, a geometric sequence, well, a sequence is called a geometric sequence if the ratio of any two consecutive terms is always equal to the same ratio, the same number, called the common ratio. R. Okay, so let me do a few examples. Let's do on page 656. Problem number 1. In exercises 1 through 5, find the first 5 terms of the geometric sequence with using the given information. So the first term is 1. and the common ratio is -2. And so the first term is 1 multiplied by -2 to get -2 times -2, 4 times -2 times -2. And so that's the first 5 terms. Let me do problem number 3. The first term is -2 and the common ratio is 3. And so -2 times 3 times 3 times 3 times 3. And so that is the first 5 terms of this geometric sequence. Let me do problem number 5. The first term is 5. And oh, well, I should really tell you this. So let me give you the formula for the general term. For a geometric sequence. So the formula is a sub n is equal to a sub 1 r to the n minus 1. And this is true for all natural numbers n. Here I'm assuming that r is not equal to 1. I'm sorry, well, r is not equal to 0. Okay, so let's show this. And I'm going to induct on n. So let's look at the initial case. So I want to show that this formula is true when n is equal to 1. So a sub 1 r to the n minus 1 is a sub 1 times r to the 0. Well, I'm assuming here that r is not equal to 0. And so r to the power 0 is just 1. So this is equal to a sub 1. And that's what I was trying to show, that a sub n is equal to a1 times r to the n minus 1 when n is equal to 1. So let me do the induction case. So let me assume that this formula is true for k, for a natural number. Okay, so let k be any natural number. Then a sub k plus 1 is equal to r times a sub k. That's by the definition of being a geometric sequence. And so ak plus 1 is equal to r times, well, by the assumption, a sub k is just a sub 1 r to the k minus 1. Okay, so let me multiply this. Well, I have r to the first times r to the k minus 1 is, well, just add. Now let me rewrite this exponent. Instead of as 1 plus k, let me write as k plus 1 minus 1. And well, that shows that the formula works. The formula works for a sub k. Therefore, by the principle of mathematical induction, a sub n equals a1 r to the n minus 1 for any real number k, any natural number n. And so that's what I wanted to show. So now let me do problem number 5. Okay, so problem number 5 says the first term is 5. It says that the ratio of A4 to A2 is 16, and that A sub n is always positive. So the first term is 5, is equal to 5. The ratio of A sub 4 to A sub 2 is 16, and we're given that all the terms are positive. Okay. So by the formula for the general term of a geometric sequence, I have a sub n is a1 r to the n minus 1. And so a sub 4 is a1 r to the 4 minus 1. So a sub 4 is a sub 1 r cubed. A sub 2 is a sub 1 r to the 2 minus 1. And so a sub 2 is a1 r. And so I have that the ratio of a sub 4, which is a sub 1 r cubed, to a sub 2, which is a1 to the r, that should equal 16. Well, assuming a1 is not 0, which we have assumed here, that a sub 1 is not 0 because we're assuming all the terms are positive. So I can cancel. And so I get that r squared is 16. So r is equal to plus or minus the square root of 16, which is 4. But r must be greater than 0. Otherwise, not every term will be positive. And so let's figure out what the sequence is. So the first term is 5 multiplied by 4, 20, multiplied by 4, 80, multiplied by 4, 320, multiplied by 4, etc. Oh, well, multiplied by 4, 1280. And that's the first 4. Oops, only first 4 terms. I want the first 5 terms. So multiply by 4. Multiply by 4, 32. By 4. And so, 2, 4, 5. Oh, I did have 5. And so, the first 5 terms of the sequence are, well, 5 times 4, 20 times 4, 80 times 4, 320 times 4, 1280. Let me do problem number 7. A sub 2, 18, a sub 5, negative 486. And so, I know that the general term a sub n is a sub 1 r to the n minus 1. Therefore, a sub 5, which is negative 486, is a sub 1 r to the 5 minus 1. And a sub 2 is 18. So in here it's 2. So you get 18 is equal to a sub 1 r. So the ratios must be equal. So I get that r cubed is let's do this. Oops. Maybe not. So let's do negative 486 divided by, oh no, I even forgot, 18 equals negative 27. Good. So r is equal to cube root of negative 27, negative 3. Let's determine what a sub 1 is. Well, I know that 18 is equal to a1 r. Divide both sides of your equation by negative 3. So a sub 1 is equal to negative 6. So let me write out the first, problem 7, 5 terms of this sequence. So negative 6 times negative 3, 18, times negative 3, negative 54, times negative 3, 162, times negative 3, so that's the first 5 terms of this sequence. To problem 9. One, 2, 4, 8. In exercises 9 through 14, find the general term for the given geometric sequence. So I know that a sub n is equal to a1 r to the n minus 1. So a sub n is equal to a sub 1, well, the first term is 1, times r. R in this case is 2 because you multiply each term by 2 to get the next term. 1 times 2, 2 times 2, 4 times 2, 8. And so a sub n is just equal to 2 to the n minus 1. 11. Four, 12, 36, 108. So this is a geometric sequence. A sub n is equal to a1 r to the n minus 1. The first term is 4. The common ratio is 3. And so a sub n is 4 times 3 to the power n minus 1. 13. 4, 2, 1, 1/2, 1/4. So again, a sub n, a sub 1, r to the n minus 1. So the first term is 4. The common ratio is 1/2 raised to the power n minus 1. And so that is the formula for the general term of this particular geometric sequence. Let me do problem number 15. In exercises 15 through 17, find the geometric mean of the numbers. So to find the geometric mean, you're going to have to multiply each number together and then take the nth root of the corresponding answer. Since there are only 2 numbers, we'll be taking the square root. The square root of 36 is 6. So you can think of this as follows, that you have somehow inserted some number to make the sequence into a geometric sequence. And so where the first number is given and the last number is given. And so 4 times 3 halves is 6. 12 halves, which is 6, times 3 halves is 18 halves, 9. So I've just inserted this geometric mean between the numbers 6 and 9, meaning that between the numbers 4 and 9, meaning that the numbers 4, 6, and 9 now form a geometric sequence. Let me do problem number 17. I want to find the geometric mean of the numbers 2 and 18. And so the geometric mean is just the square root of 2 times 18, which is 6. Problem 19. Insert 3 geometric means between 3 and 27. So I want to insert a geometric mean. I guess I'll call this a sub 2, another geometric mean, and another geometric mean. So that you have 3 geometric means between, between 3 and 1 over 27. Okay, so let's do this. So I know that a sub n is equal to a sub 1 r to the n minus 1. So I want to figure out what r is. Well, the last term, which is a sub 5, 1 over 27, is a sub 1 r to the n minus 1, 5 minus 1. So that says that a1 r to the 4 of course a1 is 3 because the first term is 3. And so divide both sides of your equation by 3, so you get 1 over 81. And so r is equal to, you don't want really negatives inside the geometric mean. So I want to assume that r here is always greater than 0, in which case I just get 1/3. Okay. And so the sequence is 3 times 1/3 times 1/3 times 1/3 times 1/3. And so the 3 geometric means have been inserted between 3 and 1 over 27. 21. 4, 12, 36, 108, and finally 8,748. Okay, so let's try to figure this out. So I know that a sub n is equal to a sub 1 r to the n minus 1. And so the last term, we'll call that the nth term, is 8748. The first term is 4. The common ratio, well, we keep multiplying by 3. Okay, so let's divide both sides of my equation by 4. And so let's do 87/48 divided by 4. 2187. Okay. Oh, I'm sorry. And so I have 3 to the power n minus 1. No, I forgot the number. 2187. 2187. Okay. Let me take ln of both sides of my equation. So you get n minus 1 ln 3 equals ln 2187. Multiply the ln 3 inside the parentheses. So by its derivative property, n ln 3 minus ln 3 ln 2187. Add ln 3 to both sides of your equation. Divide by ln 3. So n is equal to ln 3 plus ln 2187 over ln 3. And so let's simplify that. ln 3 plus ln 2187 okay. Now and then divide everything by ln 3. The only thing is I have to insert what the heck? I have to insert parentheses. Okay, that's in the parentheses. And so you get 8. So there are 8 terms in the sequence. Let me do problem 23. negative 3, 6, 12, oh, positive 6, 24, 1536. Okay, so let's figure out how many terms there are. A sub n is a1 r to the n minus 1. And so the first term is negative 3. The common ratio is negative 2. So to go from negative 3 to 6 multiplied by negative 2, multiply 6 by negative 2, negative 24, negative 12 times negative 2, positive 24, times negative 2, negative 48, etc. Okay, and I have that this last term is 1536. So let's divide both sides of my equation by negative 3. So 1536 divided by 3 oops, is negative 512. And so this is negative 2 to the n minus 1, negative 2 to the 9. Let's just check that. Negative 2 to the power 9 is indeed negative 512. And so, since the exponential function is injective and the bases are the same, then the exponents must be equal. So n is equal to 10. So there are 10 numbers in this sequence. 24, so 25. In exercises 25 through 28, draw the graph of the given geometric sequence. So negative 2, 2, negative 2, 2, negative 2. Okay, so let me graph this. Okay, so at 1 it's negative 2, at 2 it's positive 2, at 3 negative 2, 4, 2, 5, negative 2. And that's the graph of your function. Oh, let me not call it x. Let's call it n. And let's call this a sub n, your output. Okay, so that's 1, 2, 3, 4, 5. Let's do problem number 27. One, negative 2, 4 and negative 8. Okay, so let's draw this. Oh, again, I guess I'll call it, oops, n and a sub n. So at 1, 2, 3, 4. So at 1, it's 1. At 2, it's negative 2. At 3, it's 4. 2, 3, 4. At 4, it's negative 8. One, 2, 3, 4, 5, 6, 8. So at 4, it's at negative 8. Okay. And so that finishes off section 15.4, and I guess I'll do section 15.5 tomorrow. So let me save this recording.